Martin, Siddiqa, Harsha. Am I audible?
Yes, ma'am.
So, were you people able to join exactly on the timings, or you also were having trouble from the Zoom team? Because in the middle, when I started joining, it stopped responding.
Ma'am, we joined on time.
You were able to join. Okay, I don't know what had happened continuously. 40 since 45 minutes. I have been trying from another ID. It wasn't working. Let's not waste so much of time now. Already 45 minutes have been wasted. Let's start with it. Um, we have completed viscosity. Viscosity is basically the friction that occurs between the frictional force that occurs between the layers of the fluid. So the resistance that occurs, right? The resistance that occurs to oppose it. This is basically known as viscosity or viscous force. Now, see, when we are talking about viscous force, after viscous force, there is one topic which is known as Stokes' law. Stokes' law, we have studied about buoyancy, buoyant force. If I want to find out what's the viscous force that is acting on a sphere, only a sphere, we have done no the equation for viscous force. Eta, remember coefficient of viscosity was also there. What was the formula? Eta A, something related to this. Now can you recall? Eta A dV over dx. That was the formula. But for particularly sphere, we have separate formula. Suppose this is a sphere and these are the layers of the fluid. This is the radius r, let's say. So if this is moving forward with v velocity, backward there will be an opposing resistance viscous force. Fine. There will be an opposing backward viscous force acting on the body. Correct. Now see, what is the value of this viscous force that you have to remember? Viscous force on a spherical body. See, this viscous force is given by 6, a constant number, pi, you already know 3.14, eta, which is the coefficient of viscosity. R is the radius of the body and V is the velocity. This is what you have to remember about the Stokes law. This is exactly the Stokes law. Now, what exactly is the law? Law basically says that the viscous force depends upon the radius of the sphere and viscous force depends upon the velocity. So R is what? R is the radius of the body. Means this is depending upon the body. And V is the velocity of the body. So on these two things, it is depending upon. For a sphere, this particular case is for a sphere. Okay, class. This particular case, this Stokes law is valid for spherical bodies only. Viscous force on spherical body. Basically, Stokes law tells you about viscous force on a spherical body. Fine. And the constants that we'll be using 6 pi eta. All right, so what is the importance of Stokes' law? It is used in Millikan's experiment for the measurement of charge on an electron. When you will go in class 12, you have the first lesson electrostatics. There you will be studying about if a charge is, if a particle is there, oil drop is there. Millikan's experiment is basically all about oil drop, where gravitational concept, that is mg, balances the electric force. So the it is used in calculation of the charge. Why? Because oil drop is a spherical body. So that experiment you will do in detail. It accounts for the formation of clouds. It is used to find size of small particles. It explains why raindrop hurts much more than smaller one, because more the radius, more is the viscous force. This is the logic. It depends upon the velocity and the radius. These are the two things. I would suggest you to read this portion from NCERT, importance of Stokes law, a little in detail, because application based questions can come. Quickly note it down, then a terminal velocity I'll discuss with you. Stokes law is just this.
The derivation of the law is not necessary.
There is no derivation of it. There is no derivation of it as such. This was calculated only through experiments. That it depends upon this and this, on what all factors and what are the constant involved. So
Okay.
you don't have the derivation. If this derivation will come from your units and dimensions. Remember, x to the power x and v where constants are not mentioned. From there you can get where your k constant will be equal to 6 pi eta. See, now let's discuss terminal velocity. What is meant by terminal velocity? For this, let us take an example. Suppose I have taken a container. And let's say I have filled this with honey. I filled this completely with honey. Now look what happened. I have thrown a small ball. Fine. Here initially first velocity is 0 meter per second. Nothing. It's at rest. Now I have thrown it. Now once I have thrown it, it will have a certain velocity. Let's say this V2 velocity, this is 2 meter per second. Okay? Now it's going inside. Its velocity increases. It further increases to 4 meter per second. Okay. Now what am I noticing? It should increase further. 0, 2 meter per second, 4 meter per second. It should increase. I'm noticing when it is reaching this point, still the velocity is 4 meter per second. When I'm reaching this point, still the velocity is 4 meter per second. So there is a constant velocity that is achieved. Whenever this body was flowing through a viscous fluid, this was honey that I had taken. It means this is a viscous fluid, right? So there is this constant velocity which is achieved over here. This velocity is constant. So now this velocity that is achieved, this is known as terminal velocity. This velocity is known as terminal velocity. Basically, what happens here is mainly the buoyant force and your weight, mainly your weight balances. Actually, let me tell you this. Slightly, I'll tell you here because in detail we have to do this. Weight is acting, buoyant force is acting, and now if it's a viscous fluid, uh, viscous force will also be acting in the opposite direction. If it is coming downwards, viscous force will be acting upwards. Buoyant force is already there, weight is already there. So ultimately, they balance this at a certain point. After passing through, they balance this. So what happens? Upward forces become equal to the downward forces. Acceleration becomes zero. If acceleration is zero in your system, velocity will definitely be constant. That is the logic. All right, this we'll see. This is a part of your syllabus, the reasoning of it. All right, so this velocity is known as terminal velocity. So what is the importance of terminal velocity? Viscosity, importance of viscosity. Okay, this is the importance of viscosity. Viscosity importance, you all know, it's a frictional force. It's type of frictional force. This should have been added in the previous class. Okay, you people can copy it down while writing. Make just a separate point in a box so that you don't mix this up. This should have been written over there. Viscosity of air, oil, liquid is used in providing damping torque in measuring instruments. Oil used as lubricant should have proper value of viscosity. Viscosity of oil helps in applying brakes. Blood circulation through arteries depends on the viscosity of blood. These are the applications of viscosity. Leave it. Right now, let's focus on terminal velocity. So when the graph between terminal velocity versus time is plotted, it is noted, see, these are the markings of velocity, these are the markings of time. Velocity is gradually increasing, increasing with respect to time. Velocity is increasing with respect to time. And at this particular time, whatever is this time instant, velocity becomes constant. Its value is not increasing further. Plateau is reached. So this velocity which is finally achieved, you will call this velocity as the terminal velocity. Okay. Then the derivation is there. Write it down, or let's discuss the derivation together. Just write it down, then it will be at least clear. Then we'll do the derivation. Look, let us discuss now the derivation. I hope by now you all have written. All right. If anyone is writing, please stop. Look, as I told you already, weight is acting downwards, buoyant force is acting upwards, viscous force is acting upwards. Net force, basically, when terminal velocity situation arises, the main condition is that weight balances the buoyant force and the viscous force. This is the main reason behind terminal velocity, why this occurs. What is weight? Let's write in the individual terms. Weight is mg. Let's write it even in terms of density. We have taken density of the body to be rho, right? Rho, so density into volume, V into acceleration due to gravity. Fine. This is density of the body. Let's say this is first equation. Coming to buoyant force, this is equal to V sigma G, where sigma is the density of the liquid, correct? And viscous force also, this is we are talking about spherical body. So why to use the generalized formula when you already have Stokes law? 6 pi eta r v. Now what we'll do, we'll combine all these. This is the second equation, this is the third equation, correct? These are all the equations that we are having, all the three equations. Now see, one, your weight alone is balancing buoyant force and the viscous force. So at a certain velocity, which is the terminal velocity, body is in equilibrium. This is in equilibrium. This is body is in equilibrium. So put in all the values, 1, 2, 3. V sigma g plus 6 pi eta rv will be equal to V rho g. Right. Now, let's put these velocity terms, volume terms together. So 6 pi eta rv is equal to V rho g minus V sigma g. So let's take all the things that are common. 6 pi eta rv is equal to capital V into g. We have rho minus sigma. So from here, what is the value of velocity? Velocity is V g rho minus sigma. Terms that are left, 6 pi eta r, correct? Now, just one thing. Volume of a sphere, we are talking terminal velocity, we are talking about spherical bodies only. That's why I know that we are studying it under Stokes law. So if it's a spherical body, volume should be 4 by 3 pi r cube. This is a sphere, no? We have taken a sphere. If it's another body in the derivation, you will take the volume as different. But this is valid for spherical only. So sphere. Now put the volume from here. This is volume. This is volume. Put it from here. This was velocity. So volume will be 4 by 3 pi capital R cube. Here we have G rho minus sigma divided by, here we are having 6 pi eta capital R. Look, pi will be cancelled. 2 into 2, 4, 2, 3s are 6. 1 r will cancel this and make it 2. Final velocity is equation 2. From here, r square g rho minus sigma divided by, from here 3 into 3, 9 eta. This is the equation of terminal velocity. This is the derivation. This is the equation. It's simple. I hope you will be able to remember it. Nothing difficult. Just substitute this, you have to remember. Substitute all these three in this and put the value of volume. That's it. Write it down. Yes, class, if you've completed, you can leave because time is already up and portions we were not able to cover because of the delay in the class. Okay, so properly please revise this. I had to cover this entire topic. Some portions are only left, 1 or 2 questions. Okay, then in the next class we'll continue. And yes, class, I hope you have the information about this. Every Tuesday, Thursday and Saturday, you will be having 1 hour extra class for thermal portion, so that your syllabus gets completed before and we have sufficient time for revision. Because see, right now we are going at a smoother pace. We'll be doing then fluid slowly, and directly in this batch we'll start with waves and SHM. All right, we directly start with waves and SHM, this part. For these two, for these thermal properties of matter, kinetic theory, thermodynamics, 1 hour class, Tuesday, Thursday, and Saturday. Proper class it is, not an extra class or revision class. Here, the topic will be covered in this batch only. Timings 8 to 9 p.m. IST. Means I'll over the class 8 to 9, so 8 to 8:55 or 8:50, so that 10 minutes break also you will have before we start with this class. So before this class commences, that 1 hour, this class starts at 9 p.m. IST, so you have 8 to 9. Tuesday, Thursday, you already have classes with me, so 1 hour extra on Tuesday, Thursday, and Saturday you all don't have, so Saturday 1 day extra. So no classes also clashing, I think. And please attend these classes properly. Make a separate notebook for thermal unit. These 3 chapters we'll be discussing, so that in this batch we are at least covering this. So 2 things will be going simultaneously, then only we'll be able to cover the syllabus. Otherwise, last year also this occurred. I had to rush up so much in waves and SHM, and that too in the month of Feb. Let's not let it happen again. Clear, class? Anything you want to ask? I hope it's fine.
Yes,
Can you
ma'am.
repeat the
Okay.
timings?
8 to 9 p.m. IST.
Okay.
Means 1 hour before this class starts. 9 p.m. IST this class starts, our batch class. So 8 to 9. 1 hour only. But if in a week we are having 3 days class, so we'll get again 3 hours. So in 3 hours, at least let us start. Let's see how much we are able to cover by the end of December. Because let's have the syllabus completed by the month of January, then only you'll be able to revise. Otherwise, in class 11th, there is such a deficiency of time for revision classes. 12th even you have, we get time. Your revision classes also are about to start there in those 12th class batches. But 11th, lot of syllabus keeps on leaving behind. Okay, class, you can leave. Time is also getting up. Martin, you